Okay, so come back of your vacation. That's a lot of students that see me after no. But I hope you got sufficient progress on your projects. So we are nearing the end of the first part of this course, and that is actually the second part. And that is setting up the exterior calculus on a manifold. Right. So I wanted to break it up into three parts. First part of the structures that we define on the manifolds, we've got vectors, we've got tensors. The second part of setting up differential calculus on the manifold, we've more or less dealt with. This is the last interior product and the last derivative-like object we're going to be studying. And to illustrate, I'm going to rewrite classical mechanics in this differential geometric language. First, I'm going to write classical mechanics to those people. For that table, if you're not familiar with this language of Hamiltonian classical mechanics, and then we will repackage it in a coordinate invariant way, which is the geometric way. Okay. Once we're done with this, then I want to go on and talk about integration on manifolds. We're at 16 out of 30, so we're nearly halfway there. So integration itself won't take us very long, but then I want to branch out and talk about and expand on things that we notice with derivative operators, in particular the idea that d squared is 0, which defines for us a homology. So we'll talk about Iran homology and homology. We need integration for that. Once we have the integral sign, then I'll show you how the integral sign acts as like an inner product and pairs things together. It pairs forms, things that we've been talking about in integrating and differentiating. What we learned is that a form is naturally thought of as an integrand. And then the dual statement to that, the thing that gets paired with the form, is the thing that you integrate over, is what's called chains. So we pair forms and chains under the integral sign to give us real numbers. And I'll show you how chains define a homology. Same with forms define a homology. And then we'll talk a little bit about homologies. I might have to introduce some ideas about who's doing the algebra module 21. Who knows what the algebra is? Actually, please who did the lecture that? Yes. Okay. So all you guys know what the algebra is. You can least set the words. We were told whatever the algebra is, that we're just know about this. Sounds like that's like okay. So okay, so I might need to reintroduce the idea of the algebras. I'll see how it goes. There's a nice geometrical way of thinking of the algebras as well. Essentially, the lead group is a group with continuous parameterization. And if it has a continuous parameterization, then we can think of that parameterization as coordinates on a manifold. So each group, they have a differentiable manifold. And the Lie algebra is nothing but tangent space at the origin of that manifold. Now I probably go to the algebra. Okay, so I left off last time talking about the exterior derivative. We learned that the exterior derivative, but it was all the derivatives that you know of up to that point, combined into one each symbol. But it was a coordinate invariant way of thinking about the exterior derivative. That was as a map from the set of R forms to the set of R plus 1 forms. It turned out that there is another object that takes you between R forms and R minus 1 forms. And this is called an interior product called contraction. the interior product for contraction is a map. You write I x. The x there is a subscript corresponding to the vector field x. So this guy lives in several vector fields on the map for them. And it's the map between a set of R forms on ends and a set of R minus one forms. So we've already kind of hinted that the structure was there right at the beginning when we were talking about tenses. There we found that if I had an R ranked tensor, something with R in this, let's just say they're either all upstairs or either all downstairs. You can obviously define this for a PQ type tensor, but let's say I have a 0Q type tensor. I've learned that if I multiply it by some vector x, say, if I multiply it by a vector x, and I sum over repeated indices. So x is a vector, so it carries one upstairs index. If I have some type 0Q tensor that has Q downstairs indices, I'll match one of those indices, let's say the first one, with the index of the vector, right? And I sum over matched indices by the Einstein convention. Okay. So that needs to be with an object with R minus 1 free indices. So I've taken an object with, Q minus 1 free indices. I've taken an object with Q indices, and I've produced it. I've taken in an object with Q indices, and by multiplying and comparing it with the vector index, I've produced an object with Q minus 1 indices. Right? The object with Q indices downstairs, or lives in omega Q of M. The object with Q indices downstairs lives in omega Q minus 1. Right. So this contraction, otherwise known as the interior product, takes you between R forms and R minus 1 forms. Explicitly, we can write pi x on omega. This is the object now. So this is an object that I said will be an element of omega R minus 1, which means that if it's got a map, it takes R minus 1 vectors to real numbers. So it acts placeholders in here, there are R minus 1 placeholders in which I will fit R minus 1 vectors. Right. So what is this object? What is the real number that comes out of this? This number is omega acting on x. X1 to x R minus 1. Right. So there are R objects that sit in here. Makes sense because it's an element of omega R, and it maps R vectors to the real numbers. Right. And this x here is precisely this x here. So basically, you take the vector x, stick it into the first component, and you act. You take all the other vectors x1 to xr minus 1, and that is the real number that you get by acting on those vectors in omega. Same one as you get. Right. So that's the definition of what I omega is doing. And this is a coordinate independent definition, and what mathematicians would call the geometric definition, but there's also a coordinate dependent definition. So let's write that down as well. So in terms of coordinates, in terms of the components of omega and x, so in terms of components of omega and x in some standard coordinatization, Right, Ix on omega is 1 over r minus 1 factorial times x nu omega is nu mu 2 to mu r dx mu 2 raised to dx mu r. So again, let's see what we do. So I give you some R form. This has components omega mu1 to mu r. Okay, and if I write omega in terms of that R form, that is 1 over r factorial omega mu1 to mu r dx mu1 wedged due to dx mu r. The interior product of this omega, you drop the dx mu1, so you've got r minus 1 basis forms here. You contract x mu, so you contract x, the component of the vector, with the first index of mu. Right. So yeah, it seems like I'm favoring the first index. In fact, they're not, because you can write this in a more symmetric way by taking the 1 over r factorial that we get omega, summing over s equals 1 due to r x mu s omega mu 1 to mu s to mu r minus 1 to the s minus 1 dx mu 1 raised to dx mu s raised to dx mu r, and you drop dx mu s from it. Okay, so the same expression. So that's the action of the interior product. And as I've said just now, the interior product is a fancy way of saying contraction with a vector. And so if you've done 30 GR, for example, you've seen contractions before. This is the same contraction that we're talking about. Okay? And because you can build tensors from taking in products, taking tensor products of vector space. What is surprising, on the other hand, is that this interior product, the contraction of a vector index with a form index, has the properties of an exterior derivative. Right? So it has all of the properties of an exterior derivative that we identified previously. Even the fact that it's not strictly a derivative. It's a derivative that comes to the minus side depending on the degree of the form that it's acting on. So that's what we call an antiderivative. Right, so let me show you that that's the case. So Ix has similar properties to the exterior derivative. Example, suppose I have a vector and one form. X p x mu, d by dx mu, and omega mu dx mu. So standard coordinates on the manifold. In fact, let omega be a 2 form. In fact, and vector and omega to dx mu, which dx mu is omega value, and this is the 2 form. And let's see how Ix acts on this. So this is just dx mu with dx nu acting on x alpha, say the alpha. Plot the alphas because the basic form act only on the basic vector x alpha dx nu with dx nu the alpha. Which is x alpha on dx nu tensor dx nu the alpha minus dx nu tensor dx nu the alpha by the definition of the wave product. And this is just x mu d x mu dx mu dx mu minus x mu dx mu. This term here is what I would have gotten had I acted with Ix on dx mu, and then wedged with dx mu minus dx mu wedged with fx dx mu. This is a kind of trivial example of the more general case I'm playing here. And leave for you guys to go with the next exercise. If I have two forms, let's say eta R form and omega, which is an F form, then the following is two. Ix on eta with omega is Ix on eta with omega plus -1 the R eta with Ix omega. So in this sense, Ix is an antiderivative in the same way that D is. That's got the same problem. It's a bit of a pain in the butt to show because that's what we have to do. I'm in combinatorics, but I have faith in you. So this. But the upshot here is that Ix is anti-derivative. Same way as D is. What does it mean? Well, it means that if I start off with some R form, and I first act with Ix, I'll get an R minus 1 form. But then act with D, I'll get back to the space of R forms. Similarly, if I start off with an R form, act with D, I get to the R plus 1 form, act with Ix, I'll get back to R forms. So the combined action of D and of the exterior derivative and the interior product, these invariant the space that I'm working with. Okay. In fact, turns out that the sum of these two things, first act with D, then act with I, or first act with I, then act with D, is nothing but the Lie derivative. So let me show you what that's. I know, mine. So Suppose I have some one. And again, the philosophy is I make some grandiose statements. I think trivial cases and go to you, and then I'll leave the general for you, right? So, trivial case is we start off with one form, omega 1, and see what the action of this combination does. So, what does Ix Ix d plus d Ix due to this guy. I'm going to assume that X has the usual quantization X mu dx. So Ix on this one form produces for me just a fraction of the one form index to the vector index. So that's omega mu x. Okay, that's the first element. Then I have Ix acting on d of this guy. D is the anti-symmetrized derivative between the two. So this is just the mu omega mu anti-symmetrized dx mu, which is dx. Okay. G. E on this guy, this being a contraction, this is a function, is d mu of omega mu x mu dx mu plus x on this relation at the half of d mu omega mu minus d mu omega mu dx mu dx mu. I can apply the product rule here. There's omega mu d mu x mu dx mu plus d mu omega mu x mu dx mu plus x mu off goes away plus x mu d mu omega mu minus dx. Sorry, got dx mu is all of these, so take them out. The common factor of dx mu minus x mu d mu omega mu. All of this multiplied, yes. So if I look at this term cancels with this one. This leaves me with omega mu dx mu mu d nu x mu plus x mu d mu omega mu dx mu, which go back to your notes on the algebra on the d derivative. You see is nothing but the d derivative of omega, one for omega in the direction of the vector. Okay. This relation is called the infinitesimal homotopy relation because it is related to the idea of homotopies. It's initially deformable parts. The equivalence class of continuously deformable parts on the manifold, which we don't really not going to have time to come to. But in case you're find yourself in a dark alley and somebody points out to you and asks what the decimal homotopy relation, I don't know. Okay, so I said that this interior product has a lot of similar properties of D. One other property of D that I found quite important was the fact that D was Q equivalent. D squared of 0. And I alluded to the fact that we're going to spend a lot of time talking about this like this now. But because of the way that I define the interior product, it's a contraction of a vector with the anti-symmetrized indices of a form. If I contract twice, then I will have the product of two things, one of which will be symmetric, two vectors, their indices are symmetric, just flip around, and the other one will be anti-symmetric. Whenever I contract a symmetric and an anti-symmetric object, it's 0. So this means that two actions of the interior product is also vanishing, and this also, because anything that squares to 0 defines for you a homology or cohomology class structure is the same. X this is the statement that Ix is a normative operator. What potency means the following. It means that if I first take a the derivative of the form and then take the exterior, the interior product along x, same x, then by the fundamental, this is just Ix on dIx plus Ix d on omega. I said I squared was 0, so it doesn't matter if I take the exterior derivative first. This term doesn't give me any confusion. So this is just Ix d Ix on omega, which is same as Ix t plus d minus x minus one omega, which is the lead derivative of the interior product of omega. So the lead derivative of the interior product will be by similar reasoning show that the exterior derivative with the d derivative also is same one. Okay. Now let's put some of this stuff to use. And what I want to do is take all this theory that we've been developing here in Hamiltonian, show you how you can rewrite statistical mechanics in this language. And actually, there's a lot of really interesting mathematics that follows from this rewriting. It's not just a polygon. In fact, I think the last Abel Prize was given to somebody working in symplectic geometry, which is really the geometry of classical mechanics. For some reason, it was. Okay, so before I tell you about geometrizing classical mechanics, I can tell you about classical mechanics, at least in the language that we want to work with. That is to say, I want to talk about Hamiltonian classical mechanics. Now, I don't know how familiar you guys are with Hamiltonian mechanics. We've done classical mechanics. We tend to, in classical mechanics, focus on, and we might have done this in the previous class already, mathematical physics. We tend to focus on Lagrangian mechanics. So I give you this functional called Lagrangian, and associated to that functional is a set of differential equations that we solve, subject to some boundary conditions, because that's all we have. And once you know that, you know the dynamics of this. The problem with Lagrangian mechanics, as such, is that it is a second order differential equation. So typically, what you do is you set up the differential equation and then you do what you can to solve it. One of the things that you do what you can is take the second order differential equation and formulate it as two first order differential equations. Okay? And then you solve the two first order differential equations and you use one. For example, if you really like this treatment, or read Arnold's problems on classical mechanics, in which set up mechanisms underlying dynamic systems, a hell of a powerful set of tools to solve differential equations. And then you would ask, well, is there a more concise way of formulating this story? So do I not, if I forget about the fact that I'm working with some second order differential equation that I would like to solve, what is the underlying mathematics that underpins all of this? That underlying mathematics is Hamiltonian mechanics. Called Hamiltonian mechanics. And what I'll show you is that there's something even underlying that. This is the idea of symplectic geometry. Okay, so let's start then. And try and geometrize classical mechanics. So at the time that I have left today, I'm going to convey to you classical mechanics, and then we don't have lecture on Wednesday, right? I have lectures alternating Wednesday, so there should be a tough task to be done this week. But I might have, okay, I might take that task, and let's see. Well, partly because Jaco is away, but partly because I'd like to finish this one. So I might take this when there's some knowledge available. But Friday is a holiday, right?
I'm on the Monday.
What are they looking at? Yeah. Okay. Okay, then I'll definitely take them. Okay, so geometry at the testing times. Lagrangian classical mechanics has that in dynamics of some classical system is encoded in the Lagrangian functional called L, and write down in terms of the generalized coordinates and generalized velocities, the generalized coordinates using called Q instead of X, and their velocities are kilos. So it is d by dt. So dq by dt. So I give you this functional because it's function of functions. Use the functions, you got the function. This is a function of those functions. And this thing satisfies the Euler-Lagrange equations. Come from essentially taking this guy, integrating it over time, that defines for me a functional called the action functional, and then you vary that action functional. In other words, you say, what happens to that action functional if I make a small change in Q? So I go from Q to Q plus delta Q, and I ask what happens to that functional, and then I demand that that functional be zero. The variation of that functional be zero to linear order, and that gives you Euler-Lagrange equation. So this is the calculus of variations, which either you did in third year or if you didn't do in third year, let me know. I can give you my notes for to revise. It's not important because I'm not going to talk about the Lagrange mechanics. The Euler-Lagrange equations. The Euler-Lagrange equations for the system basically just say that the derivative of L with respect to Q minus d by dt of the L by dt dot is equal to 0. More generally, I can take a system which has, let's say, n degrees of freedom. So the Q's go Q1, Q3, Q2, all the way through to Qn, in which case I'll get one second order Lagrange equation for each of those variables. I can write these in a slightly different way by defining this, what I call a set of there are, let's say, n degrees of freedom. That we have n such equations, L by dt I minus d by dt of L q pi 0, then I goes 1. Okay. We can also do the following. We can define the generalized momenta associated to these q's. So q's are positions, right? They're like displacements. Associated to such displacements are momenta, right? Well, okay, so associated to such displacements are velocities, and associated to these guys are what I call conjugate variables to them. These conjugate variables are generalized momenta. So if we define the generalized momenta E I times the dl by dq I dot. Then the order of the equations basically the statement that the pi by the dt is just dl by dqi. Right, so the rate of change of momentum is minus. It's the derivative of the Lagrangian with respect to the quarter. So the first thing to note is that these other Lagrangian equations are second order. They involve two derivatives as a function is term. Typically, we tend to prefer lower order derivatives to higher order derivatives. So you can formulate this entire story in terms of a first order. That was what we call the Hamiltonian formulation of the problem. So given a Lagrangian, we can define the Hamiltonian of H. H is a function is defined to be the following: sum over all these variables, 1 to n, pk qk dot minus the Lagrangian q I q. The sum runs only over the first term. Okay. The result, though, is a function that is a function of P and Q. We trade out the velocities for the momenta by using this relation. Right. So essentially, okay, let me make 3 points. So the 3 points I want to make. First point I just said is that the left-hand side, that relation has no dependence on Q dot. We trade it out by replacing all the Q dots with their generalized momenta. So it's just a function of P and Q. This might seem like a silly observation to make because P and Q dot are related, and in most of the systems you will find that P and Q dot differ by, for example, a factor of the mass. Right? It's like saying the momentum is mv, right? And everywhere I see a v, I'll just replace it by p over n. Okay, so that seems like a silly observation to make. However, it has deep geometrical consequences. That's because this guy is a function. Okay, make one more point and then I'll is that the space coordinatized by the p's and the q's is what this is called phase space in the problem. So the space, the 2n dimensional space of PI's and QI's is called phase space of the problem. There are a number of really important realizations that come with this story. One is that for an n-dimensional system, phase space is an even dimensional space, 2n dimensional. That means I have n coordinates qi and another n coordinates pi. Okay. The other one is that the transition from classical mechanics, quantum mechanics, is best made in this language of Hamiltonian systems. It is in fact the historical way that Dirac got basically thought of in this language. What it says is that phase space becomes non-commutative. It becomes a non-commutative space, that there's some inherent underlying noise to this space that tells you that you can't define a point in the space with infinite accuracy. This idea of not defining points in the space with infinite accuracy, so the point kind of gets smudged up, is precisely encoded in the Heisenberg uncertainty relations. Okay, so all these things that are just thrown at you, I think, in undergraduate physics, are actually all tied and viewed in this geometrical way, have a really nice interpretation. Right. The third point I want to make here is that this transformation between the Lagrangian and the Hamiltonian is called the Lagrange transformation. And it's an example of what's called a point canonical transformation. And it makes sense only if the Jacobian of the transformation, the determinant of the Jacobian of the transformation is non-zero. So the transformation is sensible for the final. Determinant of d p I by d q I j. I get a matrix of determinants. I get a matrix of those partial derivatives. If the determinant of that matrix is non-vanishing, then the Jacobian of the transformation is non-vanishing, and the transformation that takes you between the Lagrangian and the Hamiltonian is a well-defined transformation. Okay. So okay. So what we're going to find in this geometrical lesson is that the Hamiltonian, right, being a function of p's and q's, and the p's and q's coordinate space, is a function map between the tangent space of phase space, at the origin, phase space manifold at the origin, and the real system. Right. And the Lagrange transformation is a transformation in the map that takes you between the tangent space and the cotangent space of the origin. So this guy, the Lagrangian, I said, trivial observation, you replace all the p's by q dots. This guy, the Lagrangian, actually lives in cotangent space, or rather, it's mapped in cotangent space of the rings. But we'll come to all of this later. For now, let me see if I can formulate the Okay, so let me see if I can formulate the equation of the motion, the second order differential equation in this language of the Hamiltonian, right? So we learned that given some Lagrange, the equation of the motion, for example, Newton's law, second law, is encoded in this second order differential equation. So for example, if you take the Lagrange to be free particles, show this exercise. So is L, it's taken to be a half q dot square. So this is the Lagrangian for a free particle. There's no potential in particle interaction, just the kinetic energy. Yeah, kinetic term. Sorry.
So since there's I think we this because we're from the two dot
Yeah. No, it's p by dq. Let me leave it there and you can think about it. Oh no, wait. You mean yeah? Yeah. Actually, I think you're right. That's right. So yeah. If I take the Lagrangian for a free particle, so free particle is just particle moving in some space. This is a half mv squared. Half mv squared is what we normally call kinetic energy from school, right? Now, if I calculate dl by dq minus d by dt of dl by dq dot, I'll find that the Lagrange equations look like this. dl by dq is 0. So this term is 0. dl by dq dot is mq dot. And then if I take another derivative of this, this says that mq double dot equals 0. So this is just a statement that if there's no forces acting on the system, then the mass times the acceleration is 0. Okay, you can say that. All right. Now, what do these equations look like in the language of the Hamiltonian? So look out the Hamiltonian. That's make an infinitesimal change in the coordinates, in phase space coordinates. So I had Q and P, UI, to I plus some small delta pi, small delta pi, and also what changes it induces in the Hamiltonian. So under this change, so I start off with some the phase space point qi here, and I make a small change to some other phase space point qi plus delta qi pi plus delta pi. What happens to the Hamiltonian? So the Hamiltonian is a function of pi and qi. So pi plus pi qi goes to h of qi plus delta pi, qi plus delta qi. And then treating this as a function of qn variables, can just use chain rule and Taylor expansion. If these deltas are small, then this is just h of pi qi plus the sum over Okay, so I'm used to notating. Let's see what I mean. dH by dPi delta Pi plus dH by delta Qi delta Qi. This here is just what we would call delta H plus, that's on my own terms, but I also know that H is given by this, the number operator. So I can also calculate what delta H is from there. And there we'll find that delta H is the sum over I of Q I dot delta Pi. So I change the Pi piece here to P plus delta P plus P I delta Q I dot minus dL by dQ I delta Q1 minus dL by dQ I dot delta Qi dot. The delta Qi dots will cancel out because of the definition of what the generalized momenta are. The Pi addresses dL by dQi dot. Which means that this is just sum over I of Qi dot delta Pi minus L by dQi delta Qi. And if I compare this expression, that expression, I find that Qi dot, that's dQi by dt, must be dH by dPi. And sorry. This guy I can replace by the Euler-Lagrange equation, which says that dL by dQi is dPi by dt. So this is minus this is just Pi dot. So this is the statement that Pi dot is minus dH by dQi. And these are the Hamiltonian equations. And you call it the same things as second order Lagrangian motion, except that they are first order, and in fact they are things that are taking place in tangent space or on state of function. So these are Hamiltonians. Rhythms. This is a good place to start. So let's stop here, and then on Wednesday I will give an example of the Hamiltonian oscillator in both Lagrangian languages, and then I will introduce the idea of a Poisson bracket, and show you how historically this was a part of classical mechanics. Basically, Poisson bracket satisfies all the properties of a bracket. And in fact, it also acts as a derivative. So start from there and in principle, you know, we build quantum mechanics from there, but we're going to go in the direction of geometry.
Yeah.